All right, we are back again. And as I mentioned on the last video, on this one, we will start to discuss about Euler's angles. Okay, we were discussing all this time, I think, in on the last 4 or 5 past videos about RPY angles, and you will notice that in order to solve for the Euler's angles, we applied pretty much the same logic that we have applied to solve for the RPY angles. Okay, so without waste any time, I will start introducing the angles. These are angles of rotation, which is made on the moving frame, which is the frame NOA. So let me write the angles. And this will be the introduction. Is a rotation. The first angle is a product of a rotation of phi about the a axis. And now this new description of the third edition. I'm using the third edition because it's in English. And as you already have noticed, sometimes I also use the second edition to solve a different example. So now it brings that the z-axis, on the z-axis of the moving frame, which is a language to tell pretty much the same thing. This moving frame is the NOA axis, and it's telling to us pretty much the same when I say that the axis is pointing on the same direction as the z-axis. So it's just a different way to tell to us the same thing. And this is the first rotation, and we got a second rotation, of theta about the o-axis. On the y-axis of the moving frame. And a third and last one, a rotation of psi about, again, about the a-axis. Z-axis of the moving frame. And right now let me just draw reference frame and this moving frame, because it's always best when we have um, these descriptions, uh, draw it visually is more easy to understand, and because we are working with um, coordinate systems. So we got this reference frame, which is we can call f x y z. Right here, the z-axis, the x-axis, and the y-axis. And the moving frame is this, what I'm calling all the time as reference frame, because if we are working with, for example, a articulated robot arm, so this arm, it has more than one link. So if it is two links, and right here is the end effector, and I'm calling this end effector, I'm attaching to this end effector a what right now what we are calling moving frame, but this is also a reference frame, um, or this one is the reference. So again, if I'm telling to you something wrong, forgive me, because as I already has said, when one frame, it turns into a reference to the other. So we are working at the same time with a reference frame, a framework. We have to know how to use the correct term on the correct context. So we will see this as we go out more deeply on this subject. So is the moving frame, and if I'm saying something wrong, throughout the series, throughout the content of the book, I can correct myself and pass to you the correct information. So we got this respect moving frame with the axis NOA, and okay, so let me write, this is the moving frame. Okay, and this one is the reference frame and also the coordinate system. And you will see that we use this as reference to come up with the solutions for the Euler's angles, just like we have done to come up with the solutions for the RPY angles. It is the only way, at least work it on the book, to solve for this angle. So this is the reference frame, and also the coordinate system. Okay, let me drag this a bit to down right here. Okay, so um, if we attach it, um, if we link it, if we link on the origin of this coordinate system of this reference frame, um, a robot arm doing a vector, which is analog right here to a robot arm. And right now, if we attach it, this moving frame, this way we are able to write a transformation. And now let's imagine that we have attached right here a 2 for certain task, and let's say is a, I don't know, a hand, and so this is the in the factor. Just doing a revision to remember how we can do this, and again we have to name these reference frames, the frames, and we also work with a universe reference frame Z, X, Y, and we name this reference frame as U. So we can write the following transformation is a transformation of the H frame in relation to the U frame, which is the same as a transformation of the H frame in relation to the R frame, because right here we are supposing that this universe frame, reference frame, we can substitute right here on this one, and R from reference frame, and in a video I had called it R because this R because of robot, and it is applicable. We got the same results, but maybe the book is the meaning on the book is reference, but Disney this we can call we can name the way that we want. Okay, okay, this is just a revision. And right now I will draw each rotation above the axis N, O, and A. So this is the moving frame, the frame that we are working, the frame in which we'll be applying these rotations. So this is the first one. So just like we have done for the RPY angles right here, actually we have using the logic that I will comment in other situations. Right now, I think I'm gonna need this. No, let me just. I will start with the reference frame and also drawing the moving frame just like on the book, and after we are as we are applying a rotation on the A frame of the moving frame, and the A frame is pointing, let me see, on the same direction as the Z frame, just like we have done all this time. We have as we are doing this analysis, so the analysis right here is to see in which direction this this axis of the moving frame is pointing in relation to the reference frame. And this way, what we have to do is got the characteristical matrix of rotation above the axis of the reference frame, and adapt to the construct a new matrix for the rotation above the respective axis in which the direction is the same. So let me illustrate this. So something like that. Sorry, X and Z. So as you can see right now, we have to do this analysis. So A is pointing on the same direction as Z. We are doing a rotation of phi above the A-axis, and as you can see, A is pointing on the same direction as Z. So what we are doing right here is a rotation of phi about the A-axis. Okay, so let's find this matrix, this characteristical matrix of rotation above this axis of the reference system. The system that it got the coordinates that we can work, in which we can work. So let me see if we can find it. Let's see where it is. Right here. Right here, the characteristical matrix of rotation above the x-axis, y-axis, and the z-axis. So let me just copy this. Let me paste right here so we can use it. So is above the z-axis, as you can see. So what we have to do right now is just adapt to the angle phi. Okay, so just need to replace for the phi angle, and right here is above the a-axis. We are constructing this new matrix phi. Okay, very simple. Okay, now this was the first rotation. So there are three rotations, and these rotations they are made it in sequence. So the first one is about the a-axis, following by another rotation about the o-axis, and the third one again above the a-axis. So it's a sequence of rotations. Let me copy this. Let me make smaller. Right now, so let me draw again the moving frame, just like on the book. So N, O, and A. And right now we are applying a rotation of theta about or above or even around the o-axis. Okay, and the o-axis is pointing on the same direction as the y-axis. So the O is pointing on the same direction as the Y. So what we have to do is, and right here, let me change this. Right here is theta. Theta. And it's about the O-axis. So again, what we have to do is to take the characteristical matrix of rotation above the y-axis and just adapt to the angle of theta. And right here is already theta. Let's just change right here for O. Okay, right. Okay, so I will have to make this a little bit bigger. Right here also. And a third and last one above the a-axis again, but with some side angle. So let me copy this. Let's just reuse this. So we won't use the characteristical matrix of rotation above the x-axis because we are not doing a transformation above the n-axis, just above the a and o. So let me draw again the moving frame. N O A, and right now we are applying a rotation above the a-axis again, but with some side angle. And right here we have just to switch for side. Okay. Okay, so we have constructed these matrices for each rotation above each respective axis. And just like we have done for the RPY angles, and we can get back just a bit to saw what we have done, and we will do the same. It's the same logic. We are applying three successive transformations of rotation, a sequence of rotations, and we have a product for these transformations, for these successive rotations right here. So right here was with some cosine of phi o, and that is wrong. If you saw in on past videos a cosine right here, so changed. Please and sorry, it's just phi o. So right here, if you are seeing a cosine of phi o, I don't know why I put right here a cosine. So right here we have to correct, it's just phi o. Okay, and right here for this RPY angles, the angles of rho, pitch, and yaw, we have a product between these angles, and doing this product, this multiplication right here, writing in form of matrices, and so we got the total transformation, sorry, the total matrix, the matrix of RPY. And just like we have done right here, we can do for Euler's angles. So first of all, we can write a transformation equation. So we can write that the Euler angles phi theta and psi is equal to, now this rotation, these transformations, a rotation above the axis with the some theta angle, phi angle, a rotation above the o-axis with some theta angle, and a rotation again above the a-axis with some psi angle. So we are able to write this transformation equation. And right now we will obtain a product, um, writing in form of matrix. And right now, what we will do is, again, what we have doing all this time till here, which is use a scale factor. So we will add a scale factor to these matrices, so we can work with these matrices on its quadratic form, so it's more easy to evaluate operations in uh, the matrix of multiplication, just because we are adding this scale factor and obtaining a quadratic matrix in which we can do operations. So this first one, let's just add a scale factor so 0 0 0 1 0 0 and 0. Okay, so let me let this clear. Adding the scale factor. Okay. Now this one, scale factor W. So 0 0 0 0, sorry, 1 0 0 and 0. Okay. And this last one with the psi angle. Zero, 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 1 0 0 and 0. Okay, now if we do the operation of products, if we multiply these matrices, we will obtain the total matrix of all order angles. And okay, so is what we will do right now. So for that, again, we will use the octave to evaluate this operation. So let's open the octave. And again, type clear all to clean the octave's memory. And CLC to clean the command window. Right here, I will come right here in window and clean the command window, edit, clear the command history. Okay. Right here we can type. We need to load the package, the symbolic package. So type pkg and load symbolic. Now we can pass to the octave the parameters that we'll use. First, you have to type sims, and now the name of the parameters. We are using data, we are using phi, and right now psi. Okay, so now press enter, and we just have to wait a little bit, and we can start to construct the matrix that we will be using. Okay, so the first matrix, let me see, cosine of phi, sine of phi, 0, 0, right here. Sine, right here is minus sine of phi, right here, let me see, sine, cosine of phi, 0, 0, 0, 0, 1, 0, 0, 0, 0, and 1. Okay, and the matrix B that we are naming B, let me just copy this. Name it B, and will be cosine of theta, right here 0, and sine of theta, sine of theta 0, right here 0, right here is 1, 0, 0, right here is minus sine of theta, minus sine of theta, 0, cosine of theta, 0, 0, 0, 0, and 1. And now C. Let's name C. So right now we have just changed this parameter for psi. Okay. Okay. Now let me just copy this and pass to the octave. now B, and now C. Now we just have to evaluate the operation A times B times C. Okay, now let me just take a print screen. And now let me write down what we obtain. And then I will compare with the book. Actually, let me just use the matrix of the book and doing the comparison at the same time. So we are analyzing this first element. Let's see if it is correct. So let's just write down this matrix. Cosine of phi times cosine of theta times cosine of psi minus sine of phi times sine of psi. And let me see. Okay, right here, minus sine of phi times sine of psi, and cosine of phi, cosine of psi, cosine of theta. Okay, this first element is correct. Now the second element of the first column, let's see, is sine of phi times cosine of phi times cosine of psi plus cosine of phi times sine of psi. Let's see, cosine of phi times sine of psi and sine of phi cosine of psi and cosine of theta. Okay, the second element is correct also. Now the third element is minus sine of theta and times cosine of psi. Okay, is correct also. In 0. Okay, so till here we got the correct elements for this first column. Now the second column is minus cosine of phi times cosine of theta times sine of psi minus sine of phi times cosine of psi. And let me see, right now we are comparing this element, the first element of the second column. And let me see, minus sine of phi times cosine of psi minus cosine of phi cosine of psi cosine of sine of theta sine of psi. Okay, is correct also. Now the second element, minus sine of phi times cosine of theta times sine of psi plus cosine of phi times cosine of psi, and is this element right now, the second element of the second column, and is also correct. Nice. And now the third element, sine of theta times sine of psi, and is correct. Okay, it's all correct. Now the third column, cosine of phi times sine of theta is correct. Perfect. And sine of phi times sine of theta. Okay, cosine of theta 0. Okay, so Octave evaluated the correct matrix. That's very nice. That's good. So we can keep on with our solution. Very nice. So this is the product that we obtain multiplying these matrices, which is the product of these successive rotations. Okay, now to the what we desired right here is to solve for these angles. We wanted to solve for these angles. So if we have a situation like we are working in a coordinate system, and we will apply these Euler angles, so we can obtain the position and the orientation if we know the solution for these angles. So right here, what we wanted to know, or even better, we wanted to solve for these angles. Is what we wanted to do. We wanted to solve for the angles phi, theta, and psi. Okay. Okay, so we have constructed the matrix of rotation above the axis on the moving frame, and we have we multiply these matrices, so with the successive transformations of rotation, and after that we obtain the following matrix. So this matrix, it represents pretty much the final position and orientation after these angles being applied. And right now, in order now is very important. So let me write in order to solve for these angles. We need to apply a inverse kinematic solution. It's more a analysis. So what we will do is the inverse kinematic analysis. So let me rewrite this. which is best? Is best um, if we said that is a inverse kinematic analysis. Right now we will do a inverse kinematic analysis. So we have already done a inverse kinematic analysis, and as the word suggests, we will work with inverse transformations, and in specific we will apply a inverse rotation again above the axis, but let me copy this transformation equation so I can do comments about it. And right here, if we apply, first of all, we have to solve this transformation equation as partitions. So on this, on the right side, if you remember, when we are working with inverse transformations, because we are exactly doing a inverse kinematic analysis, so it's directly related to inverse transformations. Right here we can do pre-multiplication. We can pre-multiply. We can use this procedure. We can be pre-multiplying or post-multiplying. Post-multiply. Right, here's post-multiply. Post-multiply. And what does that mean? It means that we can be doing the operation of multiply by the left. And if we are referring to post-multiply is by the right. And this is the inverse kinematic. We will apply a inverse transformation, and this way we can reduce this transformation equation. So let me write this also. So we apply inverse transformations to reduce the transformation equation. Okay, so is exactly what we will be doing right now. And I said that if we work with partitions, and I don't know if I was happy in saying that, but what we will do right now is multiply by the left. We are pre-multiplying, and again we are doing this in order to reduce this transformation equation, and this is the inverse kinematic solution. By the left, and we will be multiplying by the rotation, inverse rotation, inverse transformation. That is a inverse transformation, and it is above the a-axis with some phi angle, and this -1 in superscript is representing the operation of inversion. It's the inverse transformation. Okay. By the left. Okay, and if you can notice, these terms, they are equal but opposed to each other, so we can consider them, and we are left with the following transformation equation. Okay, so we have just applied the inverse kinematic solution, and this is algebraically speaking, geometrically speaking, because when we are doing this, when we do this, is also to decouple angles, but right here I'm not counting more than 3 angles. Again, if we are on the cylindrical or on the spherical coordinate system, we can count, and we are applying, if we are applying Euler's angles, we saw with the RPY angles that when we got more than 3 angles, we can we got 4 or even 5 angles. So we need to decouple these angles, and in order to decouple these angles, we apply inverse transformation. We apply a rotation above the a-axis, because the a-axis is pointing on the same direction as the z-axis, and because of this, we are able to decouple the angles when they are coupled. And this is also a inverse kinematic solution, but geometrically speaking, and right here, as you can see, is more visually, we can see more algebraically manipulation. Okay. And just like we have done for the RPY angles, we are applying we will apply RPY angles and obtain a final position, a final orientation of the angles being applied. And again, is the successive transformations of rotation with these respective angles, and after these successive transformations, we got a final position and orientation. Right here for Euler's angles is pretty much the same thing. After the successive transformations of rotations with these respective angles, we got a final position and orientation. So let me write. And something that is very important to comment that and I think I will do. Let me draw the coordinate system, the reference system, because is the system that we use to have a reference for the moving frame. Let me do something like that. X, Y, and Z. And that is the coordinate system. Is the reference system, reference frame. Okay, and so we can write that. Let me write, considering the final position and orientation on the reference frame after the Euler's angle being applied for solve for phi, theta, and psi. We can consider the following matrix. Let me see if this statement it makes sense. So considering the final position and orientation on the reference frame after the Euler's angle be applied, be applied. For solve for phi, theta, and psi, we can consider the following matrix. So nx, ny, nz, n0, ox, oi, oz, 0, ax, ay, and az, 0, and 0, 0, 0, and 1. Um, is like a generic solution for this coordinate system. Generic solution, generic matrix, generic matrix of the coordinate system. Okay. So is this one right here. And remember that I was having a problem when evaluating the operations of product, multiplying these matrices on the octave for the RPY angle. So I was getting a signal, and the signal was not correct, was not corresponding to the answer on the book, to the correct answer on the book. And I think that is because I was not considering this -1 in superscript. And right now I will try to, well, I have to do the correct resolution solution. So considering that we wanna this our desired final position and orientation, desired final position and orientation, just like we have done for the RPY angles. We will do the same right here. So this transformation matrix right here, it has the power to evaluate the solutions for these angles phi, theta, and psi. So let's see how we can do this. First of all, we have to write right now in form of matrices, and with this assumption in mind, considering the final position and orientation on this with this generic matrix of the coordinate system. So it's pretty much it looks like the matrix of the coordinate system, of the Cartesian coordinate system, but the book it doesn't mention the Cartesian coordinate system. So I'm calling a generic matrix of the coordinate system, and that is because after this solution with this, what I'm naming a generic matrix, we can apply the solutions. It must work just like for the RPY. The solution, it must work for the order coordinate system, like the cylindrical one, the spherical one. And again, we also can have a solution for this coordinate system that I have mentioned. I'm substituting right here the correspondent coordinate system, but I'm following the solution of the book. And again, the solution don't let the book don't let on the solution these exposed terms. It don't even brings the total step by step and some notations. But it's our job to know how to do this. And on today's days, you can search for anything on internet and you can find if you want. So right now we will use let's take just the rotation above the a-axis with this phi angle, and we got this rotation. We got its matrix, this one right here. So let's take and apply right now this -1 in superscript, or applying this inverse property. So right here I will just switch the signs. So right here is minus right now, and now this matrix, the generic matrix for the coordinate system, which looks like pretty much the coordinate one, but the book, it doesn't mention that it is a Cartesian one. I said coordinates again, which looks like pretty much a Cartesian one. Okay, that's it. And now the rotations above O and A, these ones, O and A, okay. Okay, that's it. And now we can start to solve for the angles to find the solutions. But first we need to multiply these matrices. And again, let's use the octave. And detail the coordinate system is the fxyz, but also we can see on this matrix the axis of the moving frame. Okay, so the book, it doesn't mention that is the Cartesian one, and it don't need to be. We can call it a generic matrix of the coordinate system. And again, is a reference system, reference frame for this moving frame. So is a reference let me write F f x y z is a reference for FNOA. Okay. So let's go to the octave, and I will need to declare the parameters again. So I don't know. I will start from the beginning. So let's see. I will clear the octave memory. Type CLC and do the process again. PKG load package load symbolic. Sorry. And now let's see. Let's just try to evaluate this left side first. So we got phi sims first. We got phi. We got nx, ny, nz. We got ox, oi, oz. We got ax, ay, az. Okay, let's try. Okay, now let's construct the matrices. So the first one is cosine of phi. Right now I will switch sinus. Right here I will switch. Right here now is minus, and right here is positive sinus. Cosine of phi. Okay, this one is ready to use. So let's copy. Okay. And now right here, I thought I get this right here. Okay, so nx, ox, I don't know if it's going to work, but I have to try it. 0, ny, oy, ay. Okay, let's try. Okay, time of the truth, a times b. And now let me take a shot of this, take a print screen. And now let me write down this and compare with the book and see if we can continue with the solution. Okay, so well, as I'm already seeing on the book, we are getting a correct solution. Let me see. Sine of phi plus ny cos. Right, very nice. Let me see. Very nice. And also the correct the sign is coming correct, which is very nice. Okay, so let me just write down, and we can continue with the solution, the resolution. Perfect. It's all right. So in x times cosine of phi plus ny times sine of phi minus nx times sine of phi plus ny cosine of phi and z and 0. Now I will need to make this smaller. Now OX cosine of phi plus OY sine of phi minus OX sine of phi plus OY times cosine of phi and OZ and 0. Now AX times cosine of phi plus AY times sine of phi minus AX times sine of phi plus AY times cosine of phi and AZ and 0 and 0, 0, 0, 1. Okay, till here we are doing all right. And now again I will clean the because I didn't declare, I don't declare psi, I don't declare data, so I need to declare all CLC PKG load symbolic. Now I'll declare again data and psi now. Theta and psi. Okay, so let's construct these matrices. So is cosine of theta, let me see, cosine of theta 0, sine of theta 0, 0, 1. This one I think is already to use. Okay, this one right here, let's name A. Let me copy. Okay, and now the matrix with psi. We can name, let's just see, and cosine of psi minus sine of psi 0, 0, sine of psi, cosine of psi, and this one is already to use. And let's just pass to the octave and now evaluate A times C. All right, let me take a shot of this. And write down and compare with the result of the book. Let me just see if it's right. Cosine of theta, cosine of psi, sine of psi, minus sine. Okay, perfect. Is right also. Okay, very nice. Minus cosine of theta times sine of psi, cosine of psi, sine of theta times sine of psi, 0, sine of theta, 0, cosine of theta, 0, 0, 0, 0, and 1. Okay. Well, right now we are ready to start to write the equations. Okay, that's it. Okay, and right now, before we start, I will just write something very important from the book. And it says that the NOA components represent the final desired values. They are normally given or known. And the values of the Euler angles are the unknown variables. Okay, right now we have just to construct the equations and try to isolate each angle, as each element on the left side of the equation, it has a equivalent element on the right side of the matrix on the respective matrix. Okay. So again, we can construct the equation trying to see what is the most obvious one that we can construct. For example, for on the left side of the equation, comparing, not comparing, but looking for its equivalent on the right side of the equation on the matrix. If we try to match the elements on the right side with which has as element the zero, maybe we will find a equation that is more easy to solve, but also the most obvious path to try to find a solution. For example, we got right here this element 0, and its correspondent on the left side of the equation is this element, and excluding the scale factor W, right here, this 0, this element is the only one as 0, so we can already write using, and let me change the color, so it's going to be, we will use this element and this element, so we can write the following equation. So ax times sine of phi plus ay times cosine of phi is equal 0. And something that I can notice, as you can see, we got an x and y, and ox or y, ax or y. So as we got this pair, and we can do a association, a analogy to the Cartesian coordinate system with these components. This is our components. With these components, these are pair. It's our pair of components, and you will see that we can do like cosine of x, sine of y. So we got a pair composed by sine and cosine, and if you wanted to know the angle, we can apply the relation tangent is equal sine divided by cosine, so we can extract applying the arctangent, and is what we will do right now. Okay, so just writing what I have just commented, we got this relation tangent is equal sine divided by over cosine. And let's see, we got right here, let's try something like that. Tangent of phi is equal to sine of phi divided by cosine of phi. Okay, so we can extract phi, if we take its arctangent, so phi is equal arctangent A10 is A10 2, because we got this pair of components AY XY, sorry, AX AY AX. And remembering, we got a complementary solution as these angles are unknown, so we don't know the orientation of the angles. I don't know if we can rewrite the equation. Something like that. We can isolate like that, and sine of phi divided by cosine of phi. Okay, something like that. And the complementary solution, which is just the components with the opposite sign of complementary solution. Okay, for phi we got the solution, and let's see. As right now we know phi, and as you can see, the left side of the equation is basically composed by the phi angles. So the left side, as we know phi, as we know phi, or left side of the equation are known. Okay, so let me change the color, and now we can write, well, right now we know phi, and that is one. This element and this element, and is a pair, right? So cosine and sine is a pair, and because of this we can apply the arctangent, apply the relation tangent is equal sine over cosine, and then we can apply the arctangent to extract the angle. So we can write let me copy this. Okay, so okay, all right. And right now is easy, very obvious, right? We already got a pair of sine and cosine component. So again, applying this trigonometric relation, tangent is equal sine over cosine. So we can write tangent of psi is equal sine of psi and cosine of psi. And psi is equal a tan to sine of psi and cosine of psi. But we got that psi is equal, now we can pass this um, here. Well, let me just write minus, well, these are two components, so it's best if we separate it between parentheses. And okay, perfect. The solution for psi. Um, and now the only remains to solve is for, we have solved it for all, we have solved it for theta. Now it remains the theta. So let's see. Again, now it's easy. On the right side of the equation, on the matrix, the elements that we can obtain to write a pair, so we can extract the angle in specific right now the theta, which is the only remaining angle to be solved. And it's very easy because we have like we don't have a composition of the element like right here, cosine of theta times cosine of psi, or sine of theta times cosine of psi. We got this pure one, so we got this 2 right here. So as we got this pair, cosine of theta and sine of theta, and on the left side it is correspondent to these elements, so it's easy to write an equation and apply the trigonometric relation. So let's do this. So ax times cosine of phi plus ay times sine of phi is equal sine of theta, and az is equal cosine of theta. Okay, all right. So again, it's just the trigonometric relation. So let me do it directly. Tangent of theta is equal sine of theta divided by cosine of theta. And we can write that theta is equal a tan 2, and now the pair is the following, a, and we have to separate. We can separate with these parentheses to better organize the solution. Okay. And we got a pair. And right here is AZ. All right. And we finish. We have solved it for our angles. We have solved it for the Euler's angles. We got solutions. And we are ready to start to solve examples. And again, these solutions, as you can see, they are composite of components yx, ax, ax, ay, az, ox, oy, az, nx, ny, and z, because we are using this generic matrix of coordinate system, as we are calling, which is the desired final position and orientation. So is composed of the reference frame and the moving frame. In this way, we can not just know where will be the final position and orientation, but also in a application in we desire to do something like track down the whole motion of the robot. It is very useful. And why we apply Euler's angles? Just like the same reason that we apply the RPY angles, because we wanted to change the initial position and orientation of a system, of a robot arm with 2, 3 in links as you wish. And also because we can with this Euler matrix, with these angles, we can restore the initial position and orientation. So basically we apply these angles to change the initial position and orientation, and also to restore the initial position and orientation of a system. Okay, so from now it's all. The solution, it was pretty much the same as we have done for the RPY. What is changed is the name of the angles, and we will see this better on the application, on the examples. We also saw again the application of the inverse kinematic analysis. So we applied the inverse kinematic analysis using a inverse transformation, and this way we are able to reduce the transformation equation. And we do this because again, right here, I'm not counting more than 3 angles. So this situation, it was not to decouple angles, but instead to reduce the transformation equation. And this way we are able to write a more simple one, and then rewrite the equation in terms of matrices. And we were assuming that the desired final position and orientation was based on this generic matrix of the coordinate system of a coordinate system. And again, after with this solution, we can also apply for other coordinate systems like the cylindrical and the spherical one. And that's it. So see you on the next video. Thank you. Bye bye.